So my name is Steve Moore. I'm a senior engineer for Atlantic Testing. I've been working here at ATL for, I think this is my 18th year. Before starting at ATL, I worked for about 10 years for an oil and gas exploration, geophysical exploration company. And ironically, a lot of the concrete NDT methods were actually originally developed as geophysical test methods. So the transition from my oil and gas days to my time here at ATL is it kind of makes sense. So here's our general outline. I'll start talking about ACI 228.2. That's concrete non-destructive test methods. There's a whole bunch of different test methods that 228.2 covers. We're going to cover 5 case studies. I think we'll have time to get through all 5 of them. I'll probably talk maybe 10 minutes or so on each one. There'll be a slide or two on some final considerations for these NDT methods that I've discussed, and really all NDT methods. Then, of course, there at the end, we're going to have our learning assessment so we can all get our credits. So what is non-destructive testing? I think all of us kind of, in our mind know what it is. I kind of stole this slide from another presentation that I do, but, generally speaking, it's a non-invasive way of determining some condition or property of a material. In this case, we're looking at concrete. ASNT describes it a little bit differently, or defines it a little bit differently. ASNT I think it's the American Society of Non-Destructive Technicians or non-destructive testing. They call it testing for discontinuities, differences, and characteristics without destroying the serviceability of the system. I don't necessarily like that word destroying, but it's destructive is it's kind of in the name. We're not so much testing without destroying the serviceability, maybe without damaging or something like that. Certainly concrete coring doesn't, assuming you're coring in the right places, it's not going to destroy the serviceability of the system. But I think a lot of us, most of us, consider coring a destructive method. So most of these NDT methods don't leave anything on the surface. There are some of them that maybe might I'll call it scar the surface or something like that. But generally speaking, they, once we're done, you can't tell that we were ever there. So I mentioned ACI 228.2. 228 is the ACI Committee for Non-Destructive Testing of Concrete. 228.2 is the document that covers a lot of different NDT methods. I've got some of them listed here. There's more than 20 of them, maybe 23, 24, something like that. And 228.2 is a great document. It's got a lot of really, really good information. Talks about the theory of a lot of the different test methods and the application of each test method. And something that's really nice in 228.2, they've got a table. This is just a portion of the table, but they give the method, talk a little bit about the principle in the table, and then they give the different applications that method can be used. The first one they talk about is visual inspection. Obviously, that's non-destructive. A lot of different things you can see just by looking at the concrete, looking at the surface, looking at the structure. But you can see here that the table's laid out pretty easy to read. The second one here, ultrasonic through transmission or pulse velocity, ultrasonic pulse velocity application, determine relative condition or uniformity of concrete based on measured pulse velocity. That's one of the methods that we're going to discuss. And that's going to be case number 1. So case number 1, we had a condition of poorly consolidated concrete out in the field. We had some really large, tall walls, 18 inches thick, some of them 20 feet or more high, large reinforcement, number 10, number 12 size bar, very congested, especially down at the bottom where you've got the dowels coming out of the footings. tying in with your vertical bars. Horizontals, there were lots of splices, and this is a containment structure. Lots of splices. Certainly horizontally, the vertical splices was really just that one down at the bottom for the most part. Low slump concrete, the initial placement certainly didn't help the situation. They also had an admixture because this was a containment structure. They put an admixture that I think it's Zypex that kind of forms these crystalline structures within the concrete that kind of helps the concrete to be less permeable. I think they call it a waterproofing admixture. I don't know if it's 100% waterproof, but it certainly brings down the permeability pretty significantly. I think that may have initially, when the project started, that may have led to some of their issues. Adding in that Zypex, it does decrease the slump a little bit. Maybe they were adding it too soon. Trucks were backed up, because it was a large placement. They had a short concrete vibrator. Obviously, the walls are 20 feet high, so you got to get down. You got to consolidate the walls. Consolidate down at the bottom. I think they had some challenges with that initially. And then they had a large free fall, 10 to 15 feet, which isn't good. I think ACI allows maybe up to 5 feet or something like that. The free fall can cause some segregation, which we saw. Some voids, honeycombing, concerns about the poor bond between the concrete and the reinforcement. You can see the picture there on the right. You can see obviously there's some voids here, and there's literally no bond between the concrete and the reinforcement there, very, very little. And segregation, as I mentioned. This right here, this is after some chipping was done, so that this wasn't, they didn't pull the forms off and see a void quite this big. But they just, there was a void there, and they kind of, did a little bit of investigating to see how bad it was. So we had some discussions with the project team, discussed some different test methods, and we decided on ultrasonic pulse velocity as a standard test method for that, C97. It is a basis for cross-hole sonic logging, which I won't be discussing today. In general, it measures the travel time of a pulse over a known distance. So we know our wall was 18 inches thick. So we know that travel distance. As 228.2 says, applicable for uniformity of concrete, which is what we're testing. Non-uniform concrete. The areas of poor consolidation and voids. That's not going to be uniform. Wave speed is proportional to the modulus, which is proportional to the strength, which is proportional to just general overall quality. So generally speaking, as wave speed goes up, your overall quality goes up. Wave speed goes down, general quality goes down. One of the things that we do when we use this test method for this application, we typically do it on a grid pattern, maybe a 1 foot by 1 foot grid pattern, maybe 2 foot by 2 foot, depending on how coarse or fine that grid pattern is. We certainly discuss that with the project team and see what their overall goals are. You get obviously finer detail with the finer grid spacing. And we did on this particular project, we did two different grid spacings, a 1 foot by 1 foot and a 2 foot by 2 foot. But one of the things that we do is we test adjacent or we analyze adjacent test points. So if we see a big variation in wave velocity over a short distance, say 1 or 2 feet, then we know there's some sort of non-uniformity there across that distance of 1 to 2 feet or whatever that point spacing is. The other thing we do is some statistical analysis, just kind of overall on the data, see what the highest wave velocity is, lowest wave velocity, the averages. We do some standard deviations to see what our range of wave velocities are. Is it thousands of feet per second, or is it, maybe just 1,500 feet per second? So that gives us a little bit of information too, just generally, what kind of range of wave velocities do we have? Which, again, kind of gives us an idea of, what our uniformity is. If you have a large range of wave velocities, then you probably have a large range of uniformity or non-uniformity. So this is an image out of 228.2. I can't draw up anything better than this, so I steal it from ACI, so to speak. Here on the left, we've got our transducers. We got on the right hand side, we've got our receivers. Wave travel path is just the length of the member. In our case, it was 18 inches. We know when the wave, the instant the wave was transmitted. We figure out the instant the wave was received, and we just figure out the velocity based on length over time. Just like miles per hour, feet per second, we typically measure feet per second. As things internal in the concrete are changing, you've got, maybe some soil intrusions if we're using the cross-hole sonic logging method, or maybe some voids or poorly consolidated concrete or some other sort of anomaly in the concrete, that's going to slow down your wave speed. Maybe there's a crack or lots of voids, and the wave speed's not going to transmit through air, so it kind of goes around the voids. Obviously that's a longer travel length, and it's going to have a longer time to travel before it's received, so it's going to give us a lower wave velocity. Or maybe in some cases the crack is so bad that we just don't receive any signal at all on the other side. But generally speaking, this is what we do. We've got a transmitter on one side, a receiver on the other side. We send a pulse, and we identify the time that it took to get from, for that pulse to travel from one side to the other. And then we generate kind of a plot like this. Depending on what our velocity distributions are, these numbers might change. In this case here, we've got 13,000 up to 16,000 plus feet per second. This particular grid was done 1 foot by 1 foot, as you can see here. This was about a 20-foot wall. We got about 18 feet up. I think this wall was about 40 feet long. So we're just looking at half of the wall. But I mentioned we compare adjacent test points. So if you look, specifically, like if you look down here at the bottom, we've got blue as our lowest wave velocity, purple is our highest wave velocity. From one point to the next, we're going from the extreme. We're going from about our lowest wave velocity to our highest wave velocity on some of these adjacent points. So these are areas that we would flag as anomalies. An area right here perhaps is an anomaly. These two spots right here, these are actually pipe penetration, so there was no data gathered here. But this would be an anomaly up here, this potentially an anomaly over here. So again, we're kind of comparing some of these adjacent test points to see, what the difference in wave velocity is over these distances, over these grid points of either 1 foot or 2 foot. So I mentioned early on, a few minutes ago about wave speed being proportional to quality and strength and modulus. One of the other things that we did on the project, or another area of the project that we did testing on was here. Also a 40-foot long wall, about 20 feet high. But you can see differences, obvious differences from, about halfway through, about 20 feet into the wall. They actually, all these 40-foot walls, they actually did in 2 separate placements. This placement here on the right, I see we've got some kind of headless dancing figure here on the right. I'm never going to get that out of my head now. But anyway, so we've got, our wave velocities here. mostly yellows and reds, maybe some greens. And then here on the left, we've got mostly blues and greens. These were actually two different placements. And when we did compressive strength testing on these cylinders, we actually got obviously two different strengths. The one on the left was about 5,000 psi. The one on the right was about 6,500 psi. So the higher the strength of the concrete, typically the higher wave velocity as well. So this does a pretty good job just highlighting the difference in wave velocity and how it compares to compressive strength. But no real anomalies here. We didn't have any big differences. Of course, this is on a 2-foot grid. This was later on in the project, later placements. Presumably the contractor, started to get their methods and procedures down a little bit better. You can see it's a little bit more uniform. Obviously, we've got some different colors in here, but no real sharp non-uniformities like we had in the previous one. So we also did some destructive testing. We took some cores at some good spots. We took some cores that weren't so good, where we had our suspected anomalies. Some probes were drilled in areas. We chipped away at some areas just to areas that we thought were some anomalies, just to see what was in there. Did the concrete, was the concrete well bonded to the reinforcement? And we found some anomalies. We found, in the core that we took in that bottom, that photo there on the left, we noted that there was an anomaly at that location. We cored that location, and we found some ping pong ball, golf ball size voids in the core. So we kind of validated some of our data there. And it's always good to, depending on the purpose of the project, the purpose of the testing, and it's sometimes good to do some destructive testing to just to kind of confirm some of your results. Sometimes it's not necessary, and we can see some of those situations a little bit later on. I think that was a pretty good application of ultrasonic pulse velocity on this project. So we're going to move on to case number 2, evaluating fire damaged concrete. We also did ultrasonic pulse velocity on this one, but kind of a different application of it. Our field conditions: we had a fire at the base of a large concrete pier. This was at a manufacturing processing facility, so they were pretty picky about pictures, so we weren't able to get too many pictures on this one. But a couple of large piers, both of them about 8 feet by 20 feet, a north pier and a south pier. The piers were originally 6 feet by 18 feet, so they added about a foot all around on each one of these piers when they changed out some of their processing equipment. So they were originally 6 by 18, but the fire was on the north side of this north pier. So this north side of the north pier got direct exposure. We did ultrasonic pulse velocity. We did some testing along this face. We also did some testing along the west face, which kind of had indirect exposure. And then we also, as kind of a control, if you will, we also did some testing here on the south pier, which really didn't have much, if any exposure. The temperature of the fire is unknown. The duration was unknown. They think it went on just about for a full shift before it was noticed. I think that's because it was at night, and they couldn't really see the smoke or anything. So not really sure how long it went on, but could have been quite a while. So ACI 228.2 talks about a way to use ultrasonic pulse velocity to check the depth of fire damage in concrete. And the idea is the damaged layer has got a lower modulus, which gives it a lower wave speed than the underlying sound concrete. And what happens is these stress waves, these ultrasonic pulse waves, they'll travel along two paths. The first path is going to be along the surface, and then the second path is along the sound underlying concrete. And what we do is we vary our transducer spacing, and we take various readings. So, we'll do it at, I think I spaced it at I don't know if it was 2 centimeters or 5 centimeters apart, but do tests at different spacings, and then you plot the wave speed versus distance or arrival times. This is also at a 228.2. So here's our transducer. We're testing on the same surface on this one. The other project we're testing on opposing surfaces. So we're not necessarily calculating wave speed here. We're just calculating travel times. So we're not calculating wave speed. So we take our transducers, we vary the spacing at closer spacings. Our wave speed, the wave is going to travel across the surface faster, and that's going to be the first arrival time of our receiver. As we space it out, as we increase our spacing, this travel time along the surface, because it's, theoretically it's damaged, it's going to have a lower wave velocity. So the faster wave speed is going to be traveling along this, this sound concrete underneath, and is going to get picked up by this receiver first. So eventually what we're going to see is our calculated wave speed is going to change. And when we plot that, the travel time versus distance, we should see two very distinct slopes. And the inverse of the slope is the wave speed. So this V sub D is actually the wave speed, or the slope. Inverse of the slope is the wave speed in the damaged concrete, and the inverse of this slope is the wave speed of the sound concrete. So that's V sub D, V sub S. And when we plot that, we get something like this. So this particular plot was on the south pier west face. So that's over here. This is the one that had no exposure. Our wave speed, calculated wave speed, was about 12,500 feet per second, which is pretty typical. 13,000 for maybe 4,000 psi concrete. If you recall our other project, we were getting up to 16,000 feet per second. That was 5,000 psi and above. But we see a relatively straight line. Now we got some bumps here and there, but for the most part, that's relatively straight. So again, this was kind of our control pier. This should be north pier. North pier west face. So this is the one that had indirect exposure right here. And you can see we kind of got some bumps in the road here. There's really no clear, it's not like we can take, the slope of this one and a distinct slope of this line, because it's kind of all over the place. We call this inconclusive. We really don't know what, I'll get back to this one, but this one didn't really provide us a whole lot of information. Then we go to the north pier, north face of the north pier. This is the one that had the direct exposure. And here we can see two relatively distinct slopes in our lines in the data. Some engineering judgment has to come into play with, which of these two, where that line break is. Probably could have included this point here. With this data set, it wouldn't have made much of a difference. But certainly over here we can see, the slope of these points is certainly different from the slope of these points here. So we know we've got different varying wave speeds. So when we do the math, when we apply this formula here, we get our the depth of the fire damaged concrete was about 2.5 centimeters. It's just easier to work in metric with these formulas and wave speeds. But 2.5 centimeters, that's an inch. I wouldn't call it insignificant, but you know, if you consider the size of these piers, you know, 8 by 20, relatively insignificant. We didn't go into, you know, our scope didn't involve any structural analysis or anything like that, but certainly one of their concerns, knowing that they put a foot of concrete around here, you know, they wanted to see if the new concrete, that new 1 foot concrete was damaged. Do they need to replace that at all? You know, and did it get down deeper than a foot? Obviously it didn't. So pretty good application of ultrasonic pulse velocity. Again, 228.2 talks about the methodology and the theory behind this one.
Steve, before we continue, first question is, what is the fire damage on the concrete and did it reduce the strength?
I missed that, Howard. Can you repeat that?
What is the fire damage on the concrete, and did it reduce the strength?
It didn't appear to reduce the strength. What is the fire damage? Fire damaged concrete typically, if anybody's seen it or read about it, it typically looks, I don't know, kind of pink colored, peach colored. And it's definitely, the surface is definitely softer. You know, you could probably scratch away with it with, you know, with a metal tool. But when I, you know, the core we're looking at here on the screen, I brought this because we did take some cores and we did do some compressive strength. We didn't know what the compressive strength was, you know, what the original design strength was. So we didn't know, you know, if it really reduced the strength or not. I think these cores came up to be over 4,000 PSI. So, you know, assuming it was probably a 4,000 PSI mix, but I brought these cores back to the office and everybody's looking at these cores and they're, you know, they're gasping at what they see at the end, you know, and they're like, boy, the concrete really burned up there at the end. Well, that's actually not burned up concrete. As I mentioned, you know, when it gets hot and burned and is fire damaged, it usually turns, you know, more of a lighter color. This core was actually taken from the surface that had the indirect exposure. So it was the west face of that north pier. And this is just a bunch of grease and stuff that is built up on the surface of the concrete. And my opinion, this is the reason why the data that we got on that face was kind of jumping all over the place. You know, I don't think we were able to get good quality data just because of the anomalies that were on the surface. You know, and you know, again, this is not fire damage here. This is an oily, greasy substance that really just kind of soaked into the surface of the concrete. And it's just kind of a, I don't know, call it a byproduct of the environment that the concrete is in. So this is not a fire damaged core. This is not what a fire damaged core looks like.
Another question, Steve, is there any value in also doing a petrographic analysis of the fire damaged concrete?
There is, and although we didn't do that on this particular project, we have done it on other projects. And a lot of times you can see the fire, you know, the fire damage. In the project, one of the projects we did it on under, I think under infrared light, we were able to see a lot of fractures, not only in the paste, but even fractures in the aggregates near the surface. So we could compare those near surface aggregates and those deeper aggregates, say at 2-3 inches, and you know, it's the same aggregate, you know, it's the same type of stone. We could see the difference under infrared light. You know, those near surface aggregates were fractured, and the deeper ones didn't show those same fractures. So yeah, there can be some value in petrographic analysis, and sometimes we might do we might do both. You know, we quite often piggyback two different test methods, you know, or multiple test methods together to give us more information. So our next case, corrosion evaluation or field conditions. This is a precast, pre-stressed parking garage. We had corrosion of the transverse beams, longitudinal deck panels. Here's you know, this top photo shows one of the transverse beams here. You can see some of the tendons exposed and even broken, you know, from spalled concrete. You know, this is one of the deck panels. It's got a spall right here on the you know, on the underside. You can see the pre-stressed tendon exposed there. So some severe corrosion on the top side and on the underside. The top side had multiple overlays. Some of the overlays were asphalt, some of them were patches. So we really couldn't do our half cell testing, which is what we did on this particular project. We couldn't do it on the surface because of those overlays on the surface. Here's a couple more photos. You know, you can see you know, these tendons exposed here. Obviously, lots of rough staining, corrosion byproduct here. Same thing here. Obviously, some cracks. You know, I mentioned sometimes doing some destructive testing to confirm your results. You know, I don't know that we needed to do any destructive testing to confirm corrosion on this particular project. But we did do some other sampling down here in this lower photo. We took some chloride samples from the beam at various steps, from 0 to 1 inch. So we just take a hammer drill and you know, basically we're pulverizing the concrete from 0 to 1 inch, and then we analyze it. And we were getting chloride results of about 1% by mass of concrete, which is a lot, considering you know, the limits are usually like 0.06 or 0.1 or something like that. But anyway, just some other photos you can see here. You know, this bottom photo, we got a huge spall right here in the center of the beam. You know, the beam, you know, this beam is shored up. They actually didn't have any traffic on this level or the level up above. You can see a bunch of the patches here, you know, which is why we really weren't able to do any of our half cell potential on the top surface. Corrosion's an electrochemical reaction, and you know, it involves a movement of electrons, and half cell corrosion potential, ASTM C76, it measures the electrical potential within the concrete, and we're measuring in millivolts, and the more negative that voltage potential is, it kind of implies that there's more electron movement. You know, remember, electrons are negatively charged, so we get that negative voltage. And you know, the more electrons that are kind of moving around, the theory is that there's more corrosion taking place at that particular location. You know, between the cathodes and anodes, with the electrons moving around. So that's why we get the negative voltage. So what we do, this is an image also out of ASTM C876. We have to physically connect one electrode to the reinforcement, and then we've got another electrode that's got a copper sulfate solution that has a known very repeatable voltage potential. And then we put that on the surface, that electrode on the surface, and then we measured the electrical potential of the concrete surface itself. You can see here in this digital voltmeter, it's got a electrical potential of, you know, negative 100 millivolts. And the more negative, again, you know, the more likely there is corrosion. So here again, we had to do it on the underside, because on the top side, you kind of have to have electrical continuity between the concrete and the reinforcement. Well, if you've got an asphalt overlay on your concrete, or even any kind of, like an epoxy overlay or something like that, you don't have that electrical continuity. And also, this doesn't work on coated reinforcement, galvanized reinforcement. There's different schools of thought there, but generally speaking, it's really not applicable to galvanized reinforcement either. But we're exposing the rebar, and we're checking the electrical potential. We do that also on a grid pattern, and that eventually gives us something like what we're seeing. We also plot this, on equipotential contour lines. And down here at the bottom, we see this table. This is right out of the ASTM. Values that are less negative than 200 millivolts implies that there's 90% or higher probability that there's no active corrosion going on. That's normal, not a whole lot of electron movement. Negative 0.2 to negative 0.35 is kind of inconclusive. That's kind of the threshold. Those are the yellow areas here. More negative than 0.35 volts, then there's a 90% or higher probability that active corrosion is occurring. So if we look at this, we see our beams, or our beams are going across the top here, kind of east-west, if you will. And then we've got our individual deck panels that span north-south. These deck panels are about 8 feet wide, I think. And I think there's 7 of them. Yeah, it looks like there's 7 of them across here, so 56 feet or so. And the corrosion's happening where we would think, right here, along the beams, kind of the joints, right? Water, kind of salt-laden water, melting and probably leaching into the concrete, causing some corrosion. So this is kind of one of the bays that we tested. This is the results here. And this was another bay that we tested. Obviously, these results are significantly different, but not surprising considering some of the photos that we saw. Right, a lot of rust stains and corrosion byproduct. And if you look at where a lot of these red areas are, it's right in between the joints, right? So the water's getting right in between the joints. Not sure how they were sealed up, or if they were even sealed up very well at all. But certainly the corrosion is happening where we would expect it to happen, just not necessarily to this degree. Looks like they had it sloped fairly well here on the edges, so water presumably flowing, and they did have some drains throughout here and there. So certainly draining draining your water, or having it pitched to a drain is a good thing. So in this particular case, like I said, we really didn't have to do any kind of destructive testing to confirm our findings. Visually we were able to kind of confirm the findings. Not really sure what the end result was. I think they ended up replacing a couple of at least one level. So our next case, concrete cover. Our field conditions, we had some precast units with running bond architectural finish. You can kind of see pictures here on the right. They were cast face down. So this exposed face here was actually cast face down. And I think there was five different types of panels. I don't know if they're 1 through 5 or A through E. But one particular panel, there was something unique about that panel and how they were securing the reinforcement at the precast facility, where they realized down the road that the reinforcement wasn't secured very well, and there was a chance that it could have shifted. And these vertical mortar joints, again, these are precast panels, so these aren't actually, they're just cast in joints, right? These aren't actual joints, but these vertical mortar joints may have had inadequate cover. So the bars cast closest to the surface were the horizontal bars, spanning across these vertical mortar joints. We use ground penetrating radar. We can get reinforcement coverage pretty good with ground penetrating radar, but the surface being so rough, we couldn't roll our GPR across the surface. So we had to figure out something else to do. Kind of put our heads together with a bunch of different people, and we came up with a solution of casting a negative, kind of match casting, a negative of the exposed surface on the mortar joints. I think there were 5 mortar joints, two on the top course, 1 in the middle, and 2 on the bottom course. So we had 5 of these panels that we cast, basically using the panel itself, using the precast panels as a mold. We cast another panel on top, and then we took those panels out to the field. We put them on top of the mortar joints, and we did our scans. We measured the thickness at the vertical mortar joint in our match panel, our negative panel, and we go out to the field and we do our scans. D1, this dimension D1 here was the thickness at the mortar joint. This was the panel that we cast here over the joint. This is that mortar joint right here. D2 is the measured depth to the reinforcement. That's what we get with our GPR. That's this distance here. And then we just simply take D2 minus D1, and that gives us our coverage. So you can see there's snow on the ground. I collected a bunch of data. There's a couple of us out there writing all the numbers down. Again, I knew what the thickness was at the mortar joint. I went to a local office, worked out of a local office for about an hour at the end of the day, punching in a bunch of numbers in an Excel sheet, and it spit out numbers where D1 equaled D2, and it spit out numbers where D1 was greater than D2. So I'm thinking to myself, all right, if D1 equals D2, then that means there is 0 coverage, right? If D1 is greater than D2, well, what does that mean? That means the bar is exposed. It's got negative coverage. So I drive 3 hours back home thinking to myself, what did I do wrong? Is this method appropriate? And what I didn't mention is we did some of this testing at the precast facility, just to kind of show to ourselves and prove to ourselves that it would work. And it worked in the precast facility, and it worked pretty good. So I'm wondering to myself, what the heck did I do wrong? 3 hours back to back home, and then 3 hours back the next day. So I knew where some of these panels were, where D1 was greater than D2, and one of them happened to be right where I parked my car the day before. So I said, all right, I'm going to go check this panel out and see what I find where D1 is greater than D2, and see if there is any exposed reinforcement, because I don't remember seeing any exposed reinforcement. So I go up to it, and sure enough, this is the width of the mortar joint here. This is a close-up picture. This is the width of the mortar joint here, and this is the epoxy-coated rebar right here. So this has negative coverage. So I felt a little bit better about what we were doing and our process and procedure, and we continued on. Not really sure what the ultimate fix was. I think they sprayed some waterproofing, some protective coatings, and I think in some of the vertical mortar joints, I think they added some material for added protection as well. But GPR is used to measure coverage pretty routinely. This was just kind of a unique application, or just kind of a unique project where we had to kind of think outside the box to figure out what we could do to measure our concrete cover. So now we're going to go on to case number 5. Field conditions. We had a concrete encased valve um, that was submerged in water. Water temperature was about 45 degrees. It was fairly consistent at 45 degrees. This was during probably right about this time of the year, if memory serves correct, spring runoff, that kind of thing. So after they place the valve's got to be shut off, and after they place the concrete, they can't open up the valve until the concrete reaches 4,000 psi. But it's submerged. It's like 40 feet, submerged 40 feet underwater. So how are we going to know when the concrete reaches 4,000 psi? We really can't use lab cylinders. If we make cylinders, bring them back to the lab and cure them in the tanks at 75 degrees or about 25 degrees Celsius, that's not going to tell us what our concrete is at 45 degrees. So, how are we going to estimate the in-place strength? Well, that's where the maturity method comes in. And the maturity method, the purpose of the maturity method is to estimate concrete strength. A couple of very, very simple concepts. Back in the early 50s, Nursall, they came up, with a statement that, any combination of curing, or a given combination of curing time and temperature results in a specific concrete strength for a specific concrete mixture. Concrete strength is a function of time and temperature. That's basically what that's saying. We know that. And we also know that cold concrete develops strength a little bit slower. So this is the Nursall equation that's part of the ASTM. There's actually another maturity equation that's part of the ASTM, but this is the most common one that's used. It's a time temperature factor, T sub A. Here in the equation, T sub A is the average concrete temperature during time interval C. That time interval can be, it can be 1 minute, it can be 15 minutes, it can be 60 minutes. Whatever that, that's the delta T. This T sub 0 is our datum temperature, which is essentially the temperature when strength development stops. ASTM says you can assume that to be 0 degrees Celsius, which makes sense. Ice isn't going to hydrate cement. But there is a method to calculate that a little bit tighter, but it's typically taken to be 0. So we add all of those up, all of these different temperatures and time intervals, and obviously that's the area under a curve, and we get our maturity function, and the units are degrees Celsius and hours, or it could be degree minutes, degree hours, degree days even, but typically degree hours. So to do the maturity method, there's kind of 2 steps to it. It starts in the lab. You got to cast a bunch of cylinders. You put thermocouples in 2 of the cylinders, and then all of the cylinders are cured the same way, at the same temperature specifically. And then we make tests at 3, 7, 14, and 28 days, maybe more often if we're looking for earlier strengths. This particular project, we took strengths more often, and we plot the maturity versus strength. And then in the field, we put the thermocouples in the field, and then we just kind of monitor the maturity for strength in the field. Typically, we'll get a curve like this. Test cylinders at day 1, 3, 7, 14, and 28. Plot that, the compressive strength and the maturity. Again, our units are degree hours. So typically get a curve like this. Our particular project we use this on, this is a curve we got. It's a beautiful curve. 4,000 psi was the strength we were looking for. We got that at about 2,000 degree hours. So we knew what our maturity value needed to be, about 2,000 degree hours. And then we got to talking with our client, and we realized, geez, we can, if we know the curing temperature, we can figure out about when it's going to reach 4,000 psi. We got our 2,000 degree hours. If we know it's at 45 degrees Fahrenheit or about 7 degrees Celsius, we just take that 2,000 degree hours, divide it by 7, you get about 286 hours, which is 12 days, which really helped the contractor to do some planning So, you know, they had an idea that in about 12 days, they were going to reach that 4,000 PSI. They could turn the valve on and you know, they could continue some other work because this was a critical path item. So, kind of two different applications of the maturity method, estimating strength, and then just kind of a happy, you know, a happy sidebar was helping them with their schedule. So, a couple of final considerations. So that's all the case studies we've got. A couple of final considerations. Just validating some of the data with cores or probes or some other you know, some other minimally invasive technique. You know, again, this kind of depends on the purpose of what you're doing. You know, that initial project that I talked about where we used ultrasonic pulse velocity. We did take some cores, we did some you know, we drilled some probes, we did some chipping, you know, so we were able to validate some of our data there. As I mentioned, each one of these methods is kind of its own unique tool. You know, combining different test methods together can kind of give you some more information depending on what your end goal might be for the project. Interpretation of NDT data can be somewhat subjective, but you know, if you got the right experience, you know, you should be able to make heads or tails of it. But sometimes you come back to the office and, you know, there was that one pier where we did the testing on where the data was kind of inconclusive. You know, we didn't have any you know, any data that really made sense or that we could hang our hat on. Sometimes that happens, unfortunately. And you know, I always try to explain to clients that that's a realistic possibility. So now we're going to get into our review questions. How are we doing on time? Pretty good. So question number one should read, should be true or false. I think these are all true or false. Impact echo test is a method used to evaluate fire damage concrete. True or false? I can take some questions during this, Howard, if any came through.
I will share them. Okay, go ahead, Steve, and answer.
Okay, that's false. Evaluating fire damage concrete, we used ultrasonic pulse velocity. I don't think impact echo would, you would not get data of any value using impact echo. Question number two, another true or false question. Wave velocity in concrete is inversely related to quality.
All right, Steve, go ahead with an answer.
So that's false. Hopefully everybody got that. Next question, true or false? The purpose of the maturity method is to estimate curing temperatures.
All right, Steve, go ahead.
And that, of course, is false. Maturity method is used to estimate concrete strength. Next one, true or false? Half cell testing is used to estimate in-place concrete strength. I do see all the answers, by the way. So hopefully, I'm throwing up some softballs here. Hopefully everybody's getting them.
All right, Steve, go ahead.
And that, of course, is false. I think this is our last one. Ground penetrating radar can be used to estimate the depth of cover, the depth of concrete cover.
All right, Steve, go ahead.
And that answer, of course, is true. That's exactly what we did on those architectural precast panels. So that's it. My contact information is there. If somebody, if anybody wants to send me an email, has any questions, we're just about out of time. I'm certainly willing to take as many questions as I can. But if anybody does have any questions, they can email me directly if you'd like.